Welcome to projectile motion. We are going to be using the equations of motion here to solve for problems of an object that is falling in response to gravity alone. All of those situations are referred to as projectiles, but we're going to start off with a very, very simple example and then gradually introduce complexity. Okay, so if you have an object and it starts at height and then falls down to the ground, then you can do some calculations. If we know the height that it fell from, then we can calculate the time that it took to fall. We can even reverse that. If we know the time it took to fall, we can calculate the height. This is a very common thing to do on bridges, for example. If you were on a pedestrian bridge and you have a small object like a small stone, you can drop the object, time how long it takes to hit the surface of the water below, and then you know the height that you were above the water. So let's do an example like that. First of all, let's remind ourselves of the equations of motion. Okay, so the first thing that I recommend that you always do is write out the word suvat so that you can annotate what it is that you do and don't know. So we're imagining that we have measured the time it took for the object to hit the surface of the water. We know that acceleration is due to gravity and we know that value. We're not interested in how fast that pebble hit the surface of the water. We do know what velocity it started at because it was dropped, and therefore it started at 0 velocity. You didn't throw it, you dropped it. And we are interested in knowing the height from the starting position to where it hit the bottom. So we want an equation that's got all of those things in, but we're not interested in V. So we don't have V, so we can't use this equation, or this one, or this one. This is the equation we're going to be using. Okay. Now, a few of my students did this a couple of years ago. There was a bridge in their town and they did this experiment and they recorded the time as being 4.6 seconds. So let's substitute that into this equation. So the value of the starting velocity is 0. It's dropped, not thrown. So because that term is 0, then what doesn't matter what t is because it's going to cancel it out. So we can actually ignore that part of the equation. And this simplifies down to that. Okay, we now need to have a think about whether we're going to write a positive number or a negative number. Now, we're interested in the amount of distance that's travelled by this object as it travels downwards. So it would be helpful if the answer came out as a positive number. So let's take down as being the positive direction. So we can just write 9.81 for gravity here. We don't need to make it negative. Time is a scalar, so it doesn't matter on the direction. So it's just going to be that number irrespective, and then squared, which gives us, to the nearest meter, 104 meters. Okay, the next level of complexity is an object that is thrown up to a height and then falls from that height back down to the ground. We have a halfway point at the top of the journey of the ball. So the object is thrown up, and at this point here, that's the halfway mark in the journey in terms of time. It's where the velocity changes direction. So we start off, for example, if we're saying that upward is the positive direction, then we start off with a positive velocity, u, and then the velocity at the top is equal to 0. It falls back down again and it hits the floor with a value v, which is equal to negative u. It's basically got the same magnitude of velocity, it's just in the other direction. It's coming down the other way. So we've got this interesting journey that is a mirror image about the point at the top. Now, often people will say things like, oh, I threw the ball, it went really, really high, it went this high, how fast did I throw the ball? So let's have a look at this type of problem. So again, we're going to write out SUVAT. The acceleration is due to gravity, we know that. We're not interested in the time. The final velocity, well, the final velocity is going to be the same as the initial velocity in terms of magnitude, but in the opposite direction. But what I'm going to do is I'm going to analyse half of the journey up to there. If somebody says, I managed to throw a ball, it went up this high, how fast did I throw it? Well, you know the height that it reached. So we have that displacement, and this is what we're interested in. We don't really care about the velocity, except for the fact that we can't do the problem without one more variable. So we're going to need to know the final velocity, and at the top of that journey, the velocity was equal to 0. So we can work out, by manipulating the problem that we're designing, we can introduce some new information. So there we have it. So the equation we're going to be using has to be this one, okay, because it's the only equation that works with the variables that we have available. Let's rearrange. And substitute. Okay, let's say that the person knew that their ball went as high as the roof of their house, and the roof of their house is 23 meters above the ground. Then we should be able to work out how hard they were able to throw the ball, how fast. To the nearest meter per second, it's 21 meters per second. Okay, we're going to look at a traditional projectile now, which is an object that has a hyperbolic shape like this, and it travels horizontally as well as vertically. Now, the very important thing to understand about this sort of problem is that the movement horizontally is independent from the movement vertically. And that's because we're dealing with a lot of vectors. Now, the ball is being decelerated vertically. It's traveling upwards fast initially, and then it slows, and then it is accelerated downwards. But the acceleration due to gravity has no effect on the horizontal motion at all. And if it's easier to think about it this way, I want you to imagine that the ball casts a shadow as it travels through its arc, and that shadow is traveling at a constant speed across the ground. So think about the sun shining down from above and casting the ball's shadow on the ground, and that shadow is moving at a constant speed. Typically in these questions, you're being asked to calculate the range of the projectile, and that range is dependent upon how much time the projectile spends in the air. Because the only thing that is going to stop this horizontal movement is the fact that the ball has hit the ground. It's no longer able to travel horizontally because it has collided with the ground, it's landed. So what we do in these types of calculations is we calculate the time that the ball has available to travel horizontally, and that is controlled by how long it takes for the ball to come up and then hit the ground again. So time is the variable that's going to connect the vertical and the horizontal movement together. Typically, you're given the starting conditions, so the angle that the object was fired or launched at, and the starting velocity. What you then have to do is you then have to resolve that into vertical and horizontal components so that you know the horizontal speed and the vertical speed. We start off by using the vertical speed to calculate how long a time it's going to stay traveling for until it lands. And then we use that to calculate how far horizontally it went in that time. Okay, so let's start off purely vertical. So we've got our object, it's going to travel up to this height and back down again. And that's how we're going to model it. So in the y direction only, let's have a look and see what information we have. Okay, so we will know the starting velocity because we can calculate it in that direction, in the y direction. If we're going to look at the entire journey, then the final velocity is going to be the same but negative. We know the acceleration due to gravity. We're not really interested in the maximum height unless we need to calculate that to get other stuff. The time is what we're interested in. Now at the minute, we don't have enough information. So let's break the journey up and have a look at the halfway mark. So here's the halfway mark. The object travels up to that height. And if we're only looking at that part of the journey, then all of a sudden we know that the final velocity is going to be 0. We could calculate the height that it reaches if we want to, but we don't need to do that. We've now got enough information. We would, though, have to double the time because we're only dealing with that part of the journey so far, and we need to double our answer for time in order to get the rest of the journey. All right, so let's pick a Suvat equation. Rearrange. And substitute. We're going to use the upward direction to be positive so that gravity is the only thing really that's likely to be negative. Okay, now we need u. So let's resolve this. It's sine okay. This number has got a lot more decimal places, and I'm going to keep them safe on my calculator. I'm only writing down a rounded value because it would be silly to write down every single number when you don't need to do that. But you will need to use the more accurate number in the calculation. The whole journey is going to be twice that. And again, I'm going to keep hold of the more accurate number in my calculator, maybe even saving it to the memory. Now that I know the amount of time that the projectile is going to spend traveling, I can put that information into the horizontal distance. Notice that this is a time, this is a scalar, so it does translate between the vertical and the horizontal. Horizontally, we're dealing with a situation where the object is moving at a constant speed and it is not being accelerated in any way. And because it's not being accelerated, we don't need to use the equations of motion. The equations of motion are for accelerated objects. If we have a quick look at them, here they are. This one has acceleration, so does this one, so does this one. The only one that doesn't is this one over here, which uses the average velocity, assuming that the initial and the final velocity are going to be different from each other. But really, that equation is just an acceleration version of this. And that's the one we want to use, because velocity at the start and velocity at the end, horizontally, are the same. So we can just use this equation. The range is equal to the velocity travelled multiplied by the time it took to travel. So we do need to resolve this into that component. So the velocity is 15 cos 50, and the time was the number that is still stored in our calculators to the nearest meter. And there's our answer. So the next type of problem introduces a level of complexity to the previous. Instead of it being an open space, we now have a barrier. And usually this is a castle wall, and you're firing either arrows or a cannon or a trebuchet at this castle, and you want to know if the projectile that you fired is going to hit the top of the wall or if it's going to make it over and get into the castle. So you have a situation like this where it's either going to make it over the top of the wall or it's not. And the way to get to the answer is to work out what the height of the projectile is going to be at the time when it reaches the wall. That's the way into this problem. So you'll be given the starting conditions. Here we go, let's make up some numbers. And you'll be given the distance between the object and the wall. You'll also be given the height of the wall so that you know how big a barrier it's going to be. And then what you need to do is you need to analyse the problem, but you need to work out how much time it takes to get to the wall, and then what height the projectile is at the wall. So it's a lot like the previous problem, but you're approaching it from the other direction. What we need to do first of all is we need to use our horizontal understanding to then plug the right numbers into the vertical to get our answer. So let's have a look at doing this. We need to calculate the horizontal before the vertical. So this object is going to travel horizontally at a constant speed, and we want to know how long a time it takes to get to the barrier. It's traveling at a constant speed, so we can just use the simplest of equations. How much time does it take to get to the barrier? The barrier is 10 meters away, and we are traveling at a velocity that needs to be resolved from this information. And once again, I'm keeping the correct number on my calculator, and I'm writing down a rounded version so that I'm not writing out 1,000 digits. So that's how long a time it takes to get to the base of the wall. Now what we need to do is we need to work out what height did the object reach after that amount of time. The object might have not quite got to that height yet, or it might have got to its maximum height and come down below that level. We don't know. So in the vertical sense, we want to know what is the height at that time. So let's analyse what information we have. We know the time that we're interested in. We know the acceleration. We're not interested in what speed it's going at. We do know what speed it starts at, and we want to know the height of the projectile at that time. So it looks like the only equation that's going to work for us is s equals ut plus a half at squared. It's the only one that doesn't have a v in it, and luckily for us we don't need to rearrange. So let's substitute in and find our answer. We need to resolve We've not assigned a direction for positive yet, but it would be quite nice because we're dealing with a projectile and it needs to get over a wall, and we're considering that wall having a positive height. So we're going to deal with upwards being positive, which means that gravity is a negative value in this. There we go. 7.2 meters. The wall being 5 meters high, it looks like we've got this kind of situation instead of this one. So the projectile does make it over the wall and inside the grounds. Okay, in this example, we're adding a different type of complexity to the regular projectile problem. In this one, we have the object being fired from a raised platform. Usually it's described as being from the top of a cliff out towards the sea. So you have the projectile and then it falls down further below the point where it originally started. Now, it's very tempting to split the journey like that and to calculate for a regular projectile and then somehow work out what's going to happen after that point, but that is an error. The halfway mark is here. So what you want to do to calculate the range of this type of projectile is you want to treat it as a problem of two halves. And the first problem is the object traveling up, and what happens is it ends up being higher than the cliffs. So you are given the height of the cliffs, and then it travels a further distance above that height. And then you can treat it like a dropped object from this new, taller height. And again, what you would do is calculate the time it took to drop from this height down there, and therefore you know how much time it is being added to the journey. So it's all to do with time. How much time did it take to get to the top? How much time did it take to fall all the way down? So we're going to need to calculate this distance and the time it took to get there. And then we're going to need to calculate the time it took to make this drop and add the two times together. And that allows us to calculate how much time it was traveling horizontally for. So this is one of the more complicated examples. So you would typically be given starting conditions. And you would have to resolve horizontally and vertically. Now vertically, we want to know about this journey up to that point. We want to know that the height that it reached above its starting position, and we want to know the time that it took to make that journey. So let's analyse what we have and how we can calculate both of those things. Now you'll notice that throughout this video I've been using this shade of purple for vertical and this shade of pink for horizontal. You may be encouraged to use subscripts, for example Y, to indicate the different components. And then when you're writing this, you would write subscript X. Okay, but if you prefer the different color method, then use the different color method. I'm going to stick with using the different colors because I've very obviously declared what it is that I'm doing, and so any examiner would see the key that I've drawn down here to indicate that which color represents which. As long as I don't mix them up at any time, it will be very clear to the examiner what I mean. Okay, so we want to know this information, but we also want to know that information. So we're going to have to do two different calculations. We'll do one at a time. For now, I'll stick with the height. So we're going to need all of the rest. We know acceleration is due to gravity. We know that the final velocity at the top is going to be 0, and we can resolve the initial velocity. So the equation for this is going to be that one. Rearrange for S. The height of the cliff is going to be expressed as a positive number in the question, so let's roll with that and say that up is positive. Resolving the vertical component. Remembering that gravity is going to be negative if up is the positive direction. I'm keeping the original number in my calculator. It does come out as a few more decimal places than this. I'm going to save it to the memory and use it later. Now let's calculate for time. So we don't want to use this value just in case we made an error during the calculation. So we're going to avoid the any Suvat equation with an S in it. Just in case there's an error, we wouldn't want one error to create an additional error and potentially lose further exam marks. Rearrange. And again, I'm going to save that number in my calculator. Now that I've got all the information that I need from this part of the journey, I'm going to analyse this part of the journey. And what I need from it is the time it takes for the object to fall from this height down to the ground, from the total height. So again, I now have the total height that I'm falling from because I've got the height of the cliff and I've got the height that it reaches. I know that the initial velocity is going to be 0. I don't care what the final velocity is going to be. I do know that it's accelerating due to gravity, and I want to find that value there. Now, because there are 2 locations where t appears, I would expect to have to use quite complicated maths in order to rearrange this for t. However, because u has a value of 0, that term disappears and the equation can be written like this instead and rearranged for t. And then we substitute. We never assigned the height of the cliff, did we? Let's say it is 27 meters high. That'll give us a nice long range. Okay, notice what I've done here. I've written acceleration as a positive number, and that's because I'm treating the heights as being positive numbers. But notice that what's really happening is the projectile is falling through that distance. It's actually moving downward. But to avoid complicating matters, I'm just going to switch up the directions just for this one calculation so that we're avoiding making everything very, very complicated indeed. Okay, and there we have our answer. Again, I'm going to save that into the memory of my calculator so that I can use the correct value in future. Okay, so we've done a lot of mathematics, we've found a lot of things out, and now what we need to do is combine the information that we have and calculate our final answer. Remember, we are looking for the range, the horizontal range. So what we needed to find out was how much time was the projectile travelling for before it hits the ground and stops its journey. We calculated the time that it took to get to the top. We've now calculated the time that it takes to hit the ground after falling from that height. So what we need to do is add those 2 times together. So here's the first one. Here's the second one. We're going to add those together, and that's the amount of time that the projectile was travelling for. So what we can use next is we can use this equation, the resolved value for initial velocity and the time that we've just calculated. And we're going to do that very quickly over here, up in the top right corner. To the nearest meter. So we previously looked at the velocity time graph for a parachutist. What we're going to do now is we're going to analyse the different parts and have a look at the forces on that parachutist. So there are different parts to this journey. We have the part where the parachutist has a velocity that is changing constantly. We have a part where the parachutist reaches terminal velocity. We have a rapidly decreasing velocity. We have another period of terminal velocity. And then we have another decrease in velocity. Okay. During this first section, we transition from where velocity is changing very rapidly to where velocity is changing very slowly. The parachutist has a constant weight throughout this time. Their weight remains the same. Initially, they have very little drag because they have a very low velocity. If you look at this axis, this is the velocity axis. We've got 0 at the bottom and we have high numbers near the top. You can see that initially the velocity is very low, and that's because they haven't accelerated very much yet. At low speeds, drag is very small. The drag cancels very little of the weight, so there is a net downward force causing the parachutist to accelerate downwards. So here is the net force with a little bit cancelled by the weight, by the drag. As they move faster and faster, as their speed increases, let's look at this section over here. What's happening is that because they're moving faster, because their velocity has increased, the drag has increased, which cancels more of the weight. So their resultant force is now still downwards, so they're still accelerating towards the ground, but they are accelerating more slowly. Their velocity is increasing, but at a slower rate. So they're still increasing their velocity. They get to this point on the graph here, where their velocity is much higher than it has previously been. Their drag is now quite high. It cancels almost all of the weight, but we still have a net downward force. When we get much higher up and we get into this flat section over here, we're at the point whereby the parachutist is travelling so fast that the amount of drag on them is almost entirely cancelling the weight. So at the end of this orange section here, where we're just transitioning into the blue section, we have no resultant force, no net force on the parachutist. They have stopped accelerating towards the ground. They have reached their maximum velocity. They are now at their maximum speed. This is called the terminal velocity. You get a terminal velocity whenever acceleration is 0. So here we have a flat section on the graph. Velocity is at its maximum. Acceleration is 0. And this is terminal velocity. The parachutists may spend a little bit of time here, but they need to get on and open their parachute. So let's look at the next section. Okay, in this section number 3, over here, the parachutist opens their parachute. So let's draw some more force diagrams. So remember that their weight is going to be the same no matter what. Now remember that they're travelling at a very high velocity at this point. And so what happens is that they open their parachute and the drag, which was at this level before the parachute, increases very, very dramatically to a very, very high level indeed. So what happens is that this drag cancels all of the weight and you're left with a resultant upward acceleration. So that is the resultant when the drag is this high. So you have an upward acceleration because there is a net upward force. And that causes the parachutist to drop from high velocity to a lower velocity. Okay? They have velocity in a downward direction. The resultant force is up, causing upward acceleration. Their velocity down decreases. They are accelerating upwards, or they are decelerating. As their velocity decreases to a lower level, the amount of drag on them decreases. Let's see what that looks like. So there's the drag. The drag is still cancelling the weight, and the resultant is now here. So you'll notice that the resultant is now smaller than it was previously. So they are still decelerating, but at a slower rate. They've gone from this velocity down to about there, and they are still decelerating. Because they are now at a lower velocity than they were before, their drag is lower. The resultant is now lower. And if we keep going and observe the pattern, they are still going at a slower velocity now, and eventually you get back to the point where the drag completely cancels the weight and you have no net force. So we've reached another point where there is no acceleration, there's no net force causing any acceleration, and you end up at point number 4. So at point number 4, velocity for somebody who is wearing an open parachute is at its maximum. Acceleration is 0, and you have another terminal velocity. So parachutists typically go through 2 sets of terminal velocities when they fall. They have the terminal velocity for a parachutist without an open parachute, and they have a terminal velocity for a parachutist with an open parachute. In step 5, that is where they would land and they would bend their knees to absorb the impact, which is still quite dramatic, and you have a very, very quick velocity decrease. Parachutists do go through specific training to make sure that they try and avoid injury as much as possible, but you can still do things like, break bones even on a regular landing if you do it incorrectly. So this is where you are landing, you bend your knees, you absorb the energy, and you have a rapid deceleration. So the important things to remember are that the faster your velocity, the greater the drag. If you have a larger surface area, then your drag will also be larger. Drag will also affect projectiles, but we don't study that at this level. So if you have calculated that a projectile fired is going to just about make it over a barrier, then you may want to consider the fact that drag will be slowing down this projectile throughout its journey. And the real path of a projectile is likely to be slightly less than what you have calculated. What you have calculated is for a situation where there is no air resistance, there is no friction from the air, there is no drag. And so this is a maximum possible theoretical position for the object to land in. What's going to happen in reality is that air friction, air drag does exist, and it will slow down the projectile and it will reduce the range that it can reach. We do also get drag forces on vehicles. So if you have a vehicle travelling, we get a driving force from the engine, and the faster the object is travelling, the higher the velocity it has, the greater the drag will be on the vehicle. And eventually what will happen is that drag will exactly equal the driving force, which means that the vehicle has reached its terminal velocity. So terminal velocities occur when we have vertical motion, but also when we have horizontal motion as well.